Okay, so PS3 is out, end of the week. You should have grades back from PS1 and you should start seeing grades for PS2. If you believe a mistake was made in grading, the procedure is to post to Piazza. And for best results, put the name of the person who graded it, which should be, you should know that from the feedback you're getting. Put the name of the person you're grading prominently, like in the title of the post and maybe the first word of the post. And post to that TA plus me, so I keep an eye on things, and then we'll get back to you. Any questions or problems about anything? Yes?
Yeah, I got marked down because I didn't test it to find out what runtime. The TA told me it was actually a different runtime, but I tested my program and I'm pretty confident I had the right runtime.
Okay, so get with a TA and make your case. I mean, if you, like I've seen, like when you timed, what was it you were timing? Oh, the anagram thing. So for example, if we were expecting to see linear time as n varies. So it's the algorithm's O of n, and for k it would be O of k log k because of the sorting. And we were expecting to see those results. But if you, for example, when you have your sets that keep track of anagrams that you've seen before or anagrams that you are keeping, so if you represent them not with sets but with, say, lists, then suddenly your runtime becomes n squared. So the key thing was to know if you measured it accurately, but we can't really know that until we see your code. So do that. Any other questions? Yes?
For like the master theorem stuff, if our extra term is n log n, how do we like determine the last term is n log n?
Okay, so we talked about something similar to that last time. You've got to put a bound on it of that's n to the d for some d. So n log n is O of n squared, but it's also O of n to the 1.5. It's also O of n to the 1.25. Yes?
So for the number of boards for like the anagrams, I got like the doubling behavior like above 2 and like less than 2.7. So I put n log m because of the doubling behavior, because it's like more than doubling. But it turned out to be like just linear and just O of n. Like, why is that? Like, why would I not get just 2?
Okay, so you're asking, you timed it and you didn't get exactly, the doubling behavior didn't tend toward 2 as n got big?
Yeah, I got like 2.4, 2.5.
Okay. Either your algorithm wasn't correct or your timing strategy wasn't precise. I mean, it has to be one or the other. I can't tell without looking. But if you had using the right algorithm and you use the timing approach that I advocated, you'll get to. I'd have to look at the code to see. Anything else? Yeah.
For our graphs, we were expected to put the ratio of
Absolutely, yes.
our times.
Yeah, you're supposed to put. I mentioned that in class. Every example I gave had either ratios or deltas depending on the situation. I even said in class that I expected you to put ratios on all your graphs. So, yeah, I've gotten a lot of pushback from some of you about that, but I think I was pretty clear about the importance of showing the doubling behavior explicitly. Any other questions? Okay. Last time. Wow. We were talking about this majority element algorithm, and let's just remember this one here. Okay, so the problem was you have an array of ints, let's say, and you want to find out if one of them occurs more than half the time in the array. And to make it fun, we're not going to do sorting or hashing or anything. The current caddis assignment that you're doing is essentially, you need a majority algorithm to solve it. I'd be extremely surprised if you managed to solve it without using a majority algorithm in the time that you have, the time limit that's imposed by caddis, because the data gets really big, and if you find yourself writing a doubly nested loop of comparing every star to every other star, that's n squared, that's just not going to work. So what was our strategy? Well, the strategy says right there, so I guess I want to ask. Split the array into halves, solve the problem for the halves, and then use those results to solve the original problem. So what was the deal? Let's see if we can remember what the algorithm was. Let me get a place to draw here. Okay, so let's say we had it's not working. It's bad. The battery died. Sorry about this. Let's try again. Drop my pen with this. Okay, let's say you have this array here. 1, 2, 1, 3, 1, 1, 5. And you want to know, does that array have a majority element, and if so, what is it? So what was the strategy? Yeah.
Split the array in half first,
Okay, so we split the array in half as best we can, so we'll try that.
then we find the majority of the left and the right side.
Okay, so we recursively find out whether that has a majority element, and if so, what is it? And similarly for that side. So when we do the recursive call over here, 1, 2, 1, 3, what's the answer going to be? No?
No.
Right. 1 is not a majority element, it's tied. Yeah?
So you split in half again.
Well, yeah, it'll get split in half, but when we make the recursive call and it's going to return an answer. What's the answer going to be? No. So the answer is no. And then we do the same thing for this array. We make the recursive call. We find out if it has a majority element. If so, what is it? And what's the answer going to be? 1. Okay, so we've got no majority element in the left half, and we've got the majority element is 1 on the right half. So what do we do? Great. 1 is the only candidate for being a majority element, the bigger of the entire array. It turns out that unless a number is a majority element of at least one of the halves, it can't be a majority element of the whole array. So we just do a single linear pass through here, counting how many 1s there are, and we find out that, yeah, there's 4 1s and only 7 elements, so 1 is a majority element. And what was the complexity of this? So the time it takes to deal with an array of size n.
And log n.
Well, let's write the recurrence. So how many recursive calls are we making? 2. And how big is each half?
Half.
All right, and over 2. And then what's after you, exclusive of the recursive calls, what do you have to do before and after? What's the cost of that? It's not constant. Linear. We have to take the majority element, or we may get 2 different majority elements that can come back. We've got to count them. And that'll take linear time because the arrays are lengthy. So we get the O in right there. And that's the same recurrence for merge sort, for example. So that's easy to see. It's just n log n. Okay. So there's a divide and conquer algorithm for dealing with the majority out problem, majority vote problem. Any questions about that? All right, let me show you another one. Here's a divide and conquer algorithm. I'll use the same array right there. And I'm going to erase a little bit here. And the way this works is, we just move, we just move left to right looking at pairs. So I'm going to look at that pair 1, 2. And what I'm trying to do is build a new array here that we're going to make a recursive call on. So I look at the pair 1, 2, and they're different, so I ignore them both. I compare 1 and 3, and they're different, so I ignore them both. I look at the 1, 1, and they're the same, and I copy 1 down. And then I have the 5 left over, so I just remember this one was left over. And there is my resulting array. So there's a linear pass where we're building a new array, and we've reduced the problem of finding a majority element of the big array to finding out if there's one of the small array. So when we make a recursive call on this, what answer are we going to get back? Does that array have a majority element? Yeah. And it's 1. So at that point, you have 2 candidates for a majority element in the original array. It's either going to be this guy here that you got as a result, or it could be the leftover one in some situations. So we just need to count and see if the 1 is a majority element or the 5 is a majority element at that point. And we get, we find out 5 is not what 1 is, and report 1 is the answer. So that's a faster version, a faster divide and conquer algorithm. Now, it's a little hard to see why that works, and you may not believe it does work. Can anyone try to think of a counterexample? Why does this pairing work? Yeah.
1, 2, 3.
Okay, hold on. 1, 2,
2,
1, 3.
1, 5, 1, 6.
Okay. So that does not have a majority element, right? It's 8 and has 4. So, and when we do our scan, these are all going to cancel out. We're going to end up with an empty array and no leftover element, and so no majority element. So yeah.
So this is kind of like the pigeonhole principle, right? Like
This is what?
It's like the pigeonhole principle. Like you have so many of, if it's a majority element, then it'll at least be in.
Yeah, so if it's, yeah, he said you can make a pigeonhole argument, but yeah, one thing to notice is if there's a majority element, you're going to end up having to pair it with itself at some point. Yeah.
If you have 2, 2, so to the 1, 2, 1, 3, 1, 5, 1, 6, and you just have like 2, 2 to the end, right?
Okay, so I had a 2, put a 2 where?
Just at the, or 2 2s at the very end.
So just add 2, 2 here?
Yeah.
Okay.
Then the array you get is just a single 2, right?
Okay, so we do the pass, we get a cancel, a cancel, a cancel, a cancel. And then there's a pair of 2s, so our new array has a single 2, and there's no leftover element. Okay, so far so good. So we recursively determine the majority element of that array, and what's the answer? No. This array has a majority element, which is 2. But what do we do with that? We don't report that necessarily as a majority element in this array. What do we do? You count at that point. All you've done is you've narrowed it down. The answer is always either going to be no, or it's going to be the majority element of that array, or it's going to be the leftover element, if there were one. So we just count the 2s, and we see that 2 is not the majority. Yeah?
What about 1, 2, 1, 3, 1, 5, 1? Just get rid of 6 and 2, 2.
Okay, so get rid of those guys?
Yeah.
Okay, so those cancel, those cancel, those cancel, and this is left over.
Count the leftover.
So we're going to find the majority element of an empty array, which doesn't have one. But the leftover element is always a possibility. So we have to, once we get the result of a recursive call, we have to count how many leftover elements there are, and we'll find out that 1 is the majority. Right, because it was left out of the pairing, so we have to give it special treatment. Yeah?
So, if we had like 2, 2, 3, 3, 5, 5, 1, you have to count all of them to make sure they're.
No. There's at most 2 numbers you have to count.
Yeah, so if we had a array of 2, 2, 3, 3, 5, 5, and the last one was 1, all of those numbers, or 3 of those numbers would be in the range. What would be left over?
Okay, so he's saying we have 2, 2, 3, 3, 5, 5, 1.
Yeah.
Okay, so we're going to, what's our array going to be for the recursive call? 2, 3, 5. What's the result of that recursive call going to be? No majority element. So we do have this leftover element that we have to count, and we'll count it, and it's not a majority either. So we're going to report that this has no majority element, which is the right answer. Yeah?
I don't know if I'm understanding this right. It seems like this would be n squared because you're moving through common.
Well, let's see what it is. So what's the cost of dealing with an array of length n?
Oh, then,
Okay, well, how many recursive calls are we making?
And over two.
Making one recursive call. How big is it?
and
No? Well,
It's dividing it into pairs, so would that mean it's essentially halving?
but it's still going for each index.
yeah, so what we're doing is a worst case problem here. So at worst, the new array is half as big as the old one. It could be smaller, right? If everything cancels out, it could be empty. But at worst, like if the worst, what is the worst case for this algorithm?
The 2, 2, 2, 3, 5, 5.
Well,
Just doubles all the way.
that's sort of the best case. If it's 1, 2, 3, 4, 5, 6, they all cancel out and there's nothing. Worst case would be all the numbers are the same. And then every other one gets copied down to the array. So anyway, you got that, and what's the overhead besides the recursive call? All right, that's a linear pass at the end. So you can see the difference is we're making one recursive call here, we made two right there. So what's log base 2 of 1? 0. So the log is 0, the exponent is 1, so the answer is just O of n to the 1. So that one's linear. Yeah?
Can you explain why there's only one recursive call?
Explain why what?
Why there's only one recursive call in front of the t's?
Okay, well let's take this array right here. We go through the array and we produce another array and make a recursive call. That's the one recursive call. Whereas the other way, we're splitting the array in half and making a call for each half. Yeah?
Can you explain what the recursion does?
Explain what recursion does?
Yeah. So after you create the array, like 2 right there, and you said you need to do a recursion.
Okay, I guess I understand your question. So,
You're saying you just call recursion on array of 2, right?
okay, I make a recursive call. So we have an algorithm. Let's say we're talking about this algorithm. The algorithm is given an array and asked, what is is there a majority element? And if so, what is it? And we reduce the problem so to answer that question, we produce this smaller array and recursively call the same method. We say, what's the majority element of this array? And if so, what is it? I mean, is there a majority element? If so, what is it?
Oh, so you're saying the base case is like,
Well, what is the base case?
if there's only one element left, that's the majority.
Well, that's one element. The base case is either one element or 0 elements, right? And if there's one element, the answer is yes, and that's it. And if there's no elements, then the answer is no.
Okay, I got it, thank you.
Okay. Yeah?
So if you have, in the new array, let's say, 2 2s and a 1,
Mm-hmm.
and then recursively calls that and determines the recursive element is 2, does it still have to go back and count the 2s, or is that the answer?
Yeah. When you make that recursive call and you get a number back, you have to make sure that number is the majority element of the big array. So the point of the recursive call is to rule out most of the numbers. So you only have to do it those 2 passes to count. Yeah?
So it was 2, 2, 3, 3, 3, 3. Does it have to come to 2 because 3 is the majority of the other small array?
No, if it's 2, 2, 3, 3, 3, 3, the recursive call will be on an array containing a 2, a 3, and a 3.
Yeah.
It'll report 3 is the majority element of the small array. Yeah, we still need to check.
You still need to check 2.
Yeah. Need to check and make sure 3 is the majority. Okay, so that's linear. Now, those are both divide and conquer algorithms. I'm going to show you another one that's not even divide and conquer. So, oops. Let's look at this one here. 1, 3, 2, 4, 1, 1, 1. How about that? So the way you can just do a single pass-through, no recursion required, to solve the majority element algorithm. And it seems like it shouldn't work, but here's how it works. You start with the first element, and that's your champion. So 1 is your champion so far, and you've seen, this is sort of the surplus number of times you've seen it. You'll see what I mean in a second. So when we see the 3, that reduces this 1 surplus to 0, and now we don't have a champion. Now we look at 2, and that becomes our new champion. And it has a count of 1. We see the 4, this 1 gets subtracted down to 0, and we don't have a champion again. Then we see the 1, it has a count of 1. We see the next one, its count goes up to 2. We see the next one, its count goes up to 3. And if after doing that process, you have a champion, then it's the majority element. So this is sort of an iterative version of that pairing off that we just looked at. And this seems like it shouldn't work. But it turns out that if there's a majority element, it'll always be the champion at the end. So can anyone think of a way to try to foil this thing? Yeah.
1, 2, 1, 3, 1, 4, 2.
1, 2, 1, 3, 1, 4, 2. Okay. There's no majority element. Well, let's make sure it says there's not one.
Right.
So we see the 1, that becomes the champion, and then the 2 cancels it out.
Okay.
1 becomes the champion, the 3 cancels it out. 1 becomes a champion, the 4 cancels it out, and you're left with a 2. You're right. Okay, I guess I was a little bit too optimistic about it, yeah. So, I remembered this wrong, apparently, that we do need to still do the check at the end. Yeah?
Oh, I thought, I think you got it, never mind. I was just gonna say, if you do the check at the end, it's still this linear plus linear.
Yeah, it'll still be linear. Okay, so, okay. Maybe that's why I found it a hard time believing it works. Yeah?
What if, in the first example, you change the first one to something else?
This one here, like make this a 4?
Yeah.
Okay, so the 4 and 3 cancel, the 2 and 4 cancel. Right, so what I had forgotten was that we need to, at the end, we're going to have 1 a champion with a count of 3. But it's still required to do a pass-through, make sure that one is. So you do the first pass to identify the champion, and then you count and make sure. Yeah?
So what was it, was 1, 2, 1, 3, 1, 1, 4.
Okay, 1, 2,
1, 3,
1, 3,
1, 1, 4.
1, 1, 4.
Yeah.
Okay, so 1 is the champion, so, all right, we get a 1, 2 brings it down. We know the 1, the 3 brings it down. Then we see a 1, so it's the champion with a count of 1. When we see this one, what happens? It now has a count of 2. Then we see the 4, which brings the count down to 1. So we still have this champion at the end. And we check, and it is the majority element.
So it only works when it is a champion, when it is a majority element?
When you identify a champion, if you don't find a champion, there is no majority element. If you do find a champion, and then you can check it and make sure it is. Yep?
Do you consider like a majority element if it's 50% of the
No, it has to be more than 50%.
Because
Yeah. Yeah.
In comparison to all the other tests that we just did, like including this one, this one wouldn't be faster than the previous tests.
Okay, this one is not, okay, so the recursive one we looked at before this one is linear. That's the best you can hope for asymptotically, because you've got to at least look at every element. This one is also linear. I suspect in practice this one would be faster, because there's just less, you don't have to build a new array, you don't have to make a recursive call. You just make 2 passes through the array and you're done. So it would be, it's still, the complexity is still linear, it's just you get faster runtime.
So this one was n squared, right?
No, this is linear.
Linear?
Yeah.
Even if we busted it there, was that
Well, we make 1 pass through, second pass through, we're done.
Oh, okay.
So it's n plus n, not n times n. Yeah?
So you only choose a new champion when the surplus counter hits 0, right?
Yeah. Yeah. Okay. Now, let me tell you a weird sorting algorithm, divide and conquer. So here's the deal. Let's take an array like 5, 1, 3, 2, 6, 4, and 0. And I'll put an 8 here and a 9 here. All right, so here's the deal for this sorting algorithm. We are going to recursively sort the final 2/3 of the array. Okay, that seems kind of off the wall, but we'll sort them in place. And what will we end up with when we do that? So we're going to have the 9, 5, 1, which are untouched, and what's going to be left when we finish the sort?
0, 2,
0, 2, 3,
4, 6.
4, 6, 8. Okay. Now, having done that, what property can you guarantee about this array?
Mostly sorted.
Well, okay, yeah, it's obvious that the high 2/3 is sorted. Let me tell you another property that it has. What can you say about the 3 smallest elements? So the third of this is length 9, there's 3 elements. So the third of the elements that make up the smallest elements in the original array, where are they guaranteed to be? First 6. So how did that happen? Let's think about it. The smallest 3 elements either have to be in this spot that we didn't touch. They could be there. For example, the 1 is. Or they had to be in the last 2/3. Once we sorted them, the 3 smallest elements have to be somewhere in this part. They can't be in this high third. You see why not? The 3 smallest elements in the array have to be smaller than the other 3 elements in this subarray. And so they'll be pushed to the left when we do that sorting pass, and the bigger ones to the right. So given that, what would be the logical next thing to do? What will happen if we sort the first 2/3 now? And we get, if we do that in place, we get 0, 2, 3, 0, 0, 1, 2, 3, 5, 9, 4, 6, 8. Okay? Now what do you know for sure? Where are those 3 smallest elements guaranteed to be now? They have to be the first 3. So by doing these 2 passes, what we've accomplished is we get the smallest third are now in their proper places. Now, how do we finish up? We just sort the last 2/3 again, and those will be put in order, and we're done with the sort. Cool. How do you think this compares with, say, merge sort or quick sort, insertion sort? What's that? Yeah? Question?
How are we sorting, you just said we're sorting the bottom 2/3, so.
Recursively.
How are we sorting?
You make a recursive call.
Just assuming the same sorting that we're
Sure.
comparing to?
Yeah, the base case would be if there are fewer than 3 elements, you just do it. I mean, if your subarray is empty, you do nothing. If it has 1 element, you do nothing. If it has 2 elements, you either leave them alone or swap them. So all this comparison and swapping happens in the base case. So what do you think? Yeah?
My opinion is that because we're kind of double sorting some elements, this would actually be slower than merge sort.
Okay. So he says with merge sort, you know, a number isn't involved in a sort more than once, but it is involved in a merge more than once. So let's say you want to know if it's better than merge sort. What do? You fire up your computer and implement it and time it? Yeah?
Can't we just check with the master theorem?
Yeah, we just write a recurrence relation and use the master theorem. So let's do that. So the time it takes to sort an array of size n is going to be what? How many recursive calls are we making? 3. And how big is, so it's 2/3 in, plus, what's the overhead, before and after the recursive call? It's constant. We're doing it all in place, so all you're doing is calculating what the thirds are. So it's O of 1. So compared to merge sort, we're making more recursive calls. The arrays are bigger during the recursive calls. But in merge sort, that'd be linear. So that term is improved. Okay? Any questions about where this came from? How I derive the recurrence relation. 3 recursive calls, each 2/3 the size of the original, plus constant. Yeah?
Sorry, can you explain why it's constant?
Well, what do we have to do? We're given that array and we got to sort it. So what's it take to make the first recursive call?
So you just grab 2/3 of the array?
Well, we don't grab 2/3 of the array. Imagine what the thing takes as, what the method takes as parameter is the array, the low bound and the high bound to be sorted. So initially it would say sort this array, start at index 0 going to index 8. So we make a recursive call that would say, okay, sort this array beginning at index 3 and going to index 8. So we don't have to copy anything. We don't have to make a new array. We just say copy this portion of the, sort this portion of the array. Then when that returns, we make another recursive call and we say go from 0 to 6. So how much work does it take to set up for the recursions? What are we having to do? A little bit of arithmetic to calculate the indexes. Don't seem convinced.
I don't. For some reason, I feel like it'd be making multiple arrays.
Okay, that's, the whole point is we're not making any more arrays. So if you want to sort an array, this method takes 3 parameters. It takes the array to sort, it takes the low bound to start the sorting at, and the high bound. So if you want to sort the last 2/3, you just pass the array the low bound of 3 and a high bound of 8. Well, that's just a coincidence that the numbers are stored there. 0, 1, 2, 3. This is index 3. This is index 8. So we just say, okay, sort this portion of the array for me. And it does. And so it just changes this array so that it looks like this array. It doesn't copy and make a new array. So all we have to do is a little bit of arithmetic to compute the bounds. I'll talk to you some more later, maybe.
Yeah.
It's important to see, though, why. I mean, I shouldn't blow this off. Why it's constant. Maybe someone else could try. Why is it constant? Why is merge sort not constant? Why does merge sort have a linear amount of work after the recursions? But you have to do a merge. There you are copying. Quick sort. Before you do the recursion, you have to do a partition. That's linear. Here, you don't do anything to the array at all. You just compute a couple indexes. Yeah?
So if merge sort was an in-place algorithm somehow, would that, like that linear term at the end, would that be O?
Well, no, because even if you could do merge sort in place, you would still have to compare in elements with each other. You have to make a pass through both sorted arrays. Quick sort's in place, but you still have to make a linear pass to partition. Yeah?
There's no comparisons being made then?
The comparisons are made in the base case. Right, there are no comparisons in the recursive case. Either before or after the recursions. You just, all you do is make 3 recursions and 3 recursive calls and you're done. All the comparisons happen in the base case.
So we're not including the base case when we're claiming that it's constant.
Well, yeah, this is the recursive case. Then to use the master theorem, you got to have a base case, and the base case needs to be constant. So what is the base case? If you get an array of size 1, 0, 1, or 2, what's the cost of sorting it? It's constant. It's just fixed length. If it's length 0 or 1, you do nothing at all. And if it's of length 2, you do a comparison and possibly one swap. So that's O of 1. Now, the base case is called a lot of times, so you end up doing a lot of comparisons. But each base case is fast. I mean, the code, I don't have the code here to show you. The recursive, it would be if the length of the array is longer than 2, one recursive call, another recursive call, another recursive call. That would be all. No ifs, nothing. You would just have a couple of expressions that compute new indexes. Else, You'd be in the base case and you do a couple, you do at most one swap and one comparison. Yeah?
How do we argue that the actual sorting is in here of the 2/3 part of the array? Because we still have to do a sort on that.
Well, we make a recursive call to sort the 2/3, yeah.
So would that recursive call still be like an n log n?
We don't account for the cost of the recursion right here. Where do we account for the cost of the recursion? Here. This is saying that the cost to sort an array of length n is 3 times the cost of sorting an array of length 2n over 3, plus a constant amount of work. Yeah?
So what's the problem with this kind of algorithm? Why is it not used more often, or is it?
Okay. Well, let's see. What we're going to need to do is use a master theorem and see what this works out to. But I want to dispose of any other questions about where this thing came from. Master theorem won't do you any good unless you can take an algorithm and produce a recurrence relation. Okay? Well, here's our recurrence. What's A? A is 3, that's the number of recursive calls. What's B?
3 halves.
Very good. They said that to drown out anyone that might have said 2/3. So let's talk about that. Why is it 3 halves and not 2/3? Yeah.
Since you divide, n is divided by 3 halves, you have
Right.
to flip it.
This looks like a 2/3 here, but we want the B is what you divide n by. So if there's just a 2, if you just had the 3 in the denominator, you wouldn't say 1/3, right? You'd say 3. N is being multiplied by 1/3. It's being divided by 3. Similarly, it's being multiplied by 2/3. It's being divided by 3 halves. So, furthermore, 2/3 would pass a sanity test, would fail a sanity test. What would be wrong with 2/3 just on the face of it?
It's less than 1.
It's less than 1. You've got to be making this problem smaller. That would make the problem bigger. And what's D?
0.
It's 0. So the key thing we got to ask now, what is the log base 3 halves of A, which is 3?
Is greater than 0.
So to what power must you raise 3 halves to get 3? Well, it's bigger than 1, because 3 halves to the first power is 3 halves. What about 2? What's 3 halves to the second power? 2.25. So it's bigger than 2, but it's less than 3. Okay? So that log is bigger than our D, so what's our answer going to be according to the master theorem? O of n to this log. So why don't people use this sorting algorithm? It's worse than n squared. It's worse than selection sort. It's O of n to the 2 point something. No, it's not even better than selection sort. It's bad. So this one is called stooge sort, after the 3 stooges. But it is a good exercise for seeing if you understand recurrence relations. Okay. Any last questions about any of these recurrence relations we've been looking at with this algorithm? Yeah?
Like when the 3 halves comes out mathematically, could you explain what it means in the context of the algorithm itself? Like where you I guess, derive 3 halves from just into the...
Okay. Okay. We had an array of length 9 that we had to sort. And we did it by sorting 3 arrays of length 6. So this is just saying that each time you make a recursive call, it's on an array that's 2/3 the length of the original. And the B in the master theorem is the thing you divide n by, which in this case is 3 halves.
It's multiplying n times 1 over b, so you get b. You have to take
Yeah. Yeah, we're multiplying by 2/3, we're dividing by 3 halves. Yeah, and you never have that problem if you've got n over 3, you'll always say, okay, b is 3, or if it's n over 2, you say b is 2. Something gets confusing when you got something like that, but it's really the reciprocal of what you're multiplying n by. Any other questions? Okay, let's take a quick break and then we'll look at something different. Okay, so we talked about caret-Suba multiplication last time. And just to remind you, the idea, it was sort of based on the idea of the recursive multiplication that we looked at. But we reduced the number of recursions from 4 to 3. So to multiply x and y, we split it into halves. And we had to multiply the left half of x by the left half of y. That was one recursive call. But the numbers are half as big at that point. We had to do was multiply the right halves. And then the tricky thing about caret-Suba is that we add xl and xr to get a number, and multiply that by yl plus yl. And it turns out from all that, you can go through these calculations and reconstruct the final answer just from those three products. Now, it looks like we're multiplying here and here, but why are these not really multiplications? They're just bit shift operations. To do times 2 to the end, you just stick n zeros on the end of the number. So that's fast. And this was our recurrence relation, and we found out it was n to the 1.59, O of n to the 1.59, which is y base 2 of 3, which is better than the n squared from the grade school algorithm. The question is, how practical is this? So that's what I want to talk about now. So what I've got here is I took the grade school algorithm, and I determined the average time to multiply pairs of n-bit integers for different values of n. And basically, I used n equals 2 to the k for different values of k. So I started with 2 to the 0, which would be 1-bit integers, and went up to 2 to the 17th, which would be, I guess, 18-bit integers. Okay, so I went up by powers of 2, so I'm doubling. So I want to see the doubling behavior. And here's the plot of the grade school algorithm. So let's try to understand why it looks that way. First of all, I want you to notice it's a log-log scale. So this is not n down here, it's log of n. So this is when n is 2 to the 1, 2 to the 2. So really this would be 0, 1, 2, 4, 8, 16, 32. Also, the vertical scale is a log as well. So it's log versus log. Why is it flat up to here? Really, I can't explain this in the dip. That makes no sense at all to me. But so ignoring that dip, it's flat all the way to there. What's going on? Yeah?
Because your hardware supports like constant multiplication of up to a certain number of bits, and once you exceed that, then you have to start using your algorithm.
Right. So I take my big number I'm multiplying, and I store it, like we talked about, an array of I don't know if probably 32-bit numbers. I forget if I use 16-bit numbers or 32-bit. Probably 32-bit numbers. And so until I get up to 32 bits, the grade school algorithm is just multiplication. You just take the 32 bits and multiply the other 32 bits, and that's one step on a computer, so it's constant time. And then when the number gets too long, that's when you're having to do a bunch of sub-multiplications and additions to get the final answer, and it becomes slower and slower. Okay? So it's the difference between, assuming you all have the multiplication table memorized, asking you to multiply 5 times 5, it shouldn't take you any longer than asking you to do 6 times 3. So maybe you're multiplying by 9s and 8s, or you're multiplying by 1s and 2s. It's going to take the same amount of time. But then when I started asking you to multiply 332 by 15, suddenly you've got to use the algorithm and you slow down. And as they get longer and longer, it gets worse and worse. Now, why is this line straight?
Is it because it's a log scale?
It's a log scale, log plot. A power of n is going to plot as a straight line, and the slope is the exponent. So the slope of this line, it's a little hard to see, but from here to here, right? We're basically going we're going up by 2, right? From 11 to 13, we're going over by 2, and how far up are we going?
4.
By 4, because this goes up by 4. So rise over the run, 4 divided by 2, it's 2. So that n squared for grade school just gives you on this log scale, it gives you a straight line. And you can read the exponent from the slope. Okay? So that's that. Here's my actual numbers. So again, this is k. And this is the actual timing it took, and this is the ratio, and you can see it tended toward the doubling behavior we expect is 4. Double the number of bits and the numbers you're multiplying, it'll take 4 times longer. The multiplication takes 4 times longer, because it's an n-squared algorithm. Okay, now I did the same thing for caret Suba. So what would you expect the plot of caret Suba to look like? Okay, smaller slope. Why would we see a smaller slope in the steady state? So I don't know what happens over here. Eventually, we're going to get a straight line. And what's the slope going to be? It's not going to be 2. It's going to be n to the log base 2 of 3, which is 1.59. So it's less of a slope. So it's growing slower, more slowly. What's going to happen at the beginning? Yeah. One thing you realize about caret Suba is, the way I defined it, it keeps subdividing the numbers till we get to 1 bit. The base case is multiply a pair of bits. Unlike grade school, which is always doing operations in chunks of machine length numbers. So grade school is nice and slow up till you get to 32 bits, and then it starts to degrade. Caret Suba does its magic all the way down to single bit. Just the way I implemented it. And you end up with this picture. So, here's where you are, and you're multiplying 2-bit number by 2-bit number. And then, there it goes. And if you stare at it, you can convince yourself, yeah, that looks like a slope of about 1.59. Where will those lines intersect? In other words, at what point does this red line become faster? Where does this become faster than this? How big does that go?
Very big.
Yeah, I mean, let's see, right here it's roughly 1, 2, 3 blocks apart, and here it was about 2.5. So it'd be somewhere on the far side of that wall where they cross. And how big will k be at that point? 100? 2 to the 100th power is larger than the number of particles in the known universe, the number of subatomic particles in the known universe. So clearly completely impractical. You would never use caret Suba. Like that, anyway. Yeah?
Would that be much better if you created an implementation that stopped using caret Suba once it got to numbers?
Yes, it would make a huge difference. So when you see something like this, you say, wow, why would I ever use caret Suba? But here's the thing. When you have a divide and conquer algorithm that's asymptotically faster than some non-recursive, it doesn't matter if it's non-recursive, but you got a divide and conquer algorithm that's asymptotically faster than some other algorithm, but is slower for all but massive ends, what you start thinking about is combining the two algorithms, try to combine their strengths. So how could you combine caret Suba with grade school to get something better than either? Yeah?
You do caret Suba until you get down to 32 years.
Okay, so one thing you could do is, you're doing caret Suba, which each time, each level of recursion, you're splitting the number in half, split the number in half, split the number in half. When you get down to your numbers of 32 bits, stop splitting them in half and just multiply them already. Okay? Now, why would that make a difference? What are you getting rid of when you stop the recursion at level at 32 bits? Think about the recursion tree. How many levels of the recursion tree are you slicing off when you stop there? Yeah, 5 levels. Any recursive algorithm, it makes huge strides. You start with 2,000 bits. In one level of recursion, you're down to 1,000 bits, and then 500. But when you get down to the bottom of the tree, you start making little tiny advancements. So a tremendous amount of the work of recursive algorithm is down near the base case. So by cutting off caret Suba, when you get down to 32 bits and just multiplying the numbers together using your machine arithmetic, it's going to speed it up quite a bit. So let's see what happens. So first of all, this is, we said before that the doubling behavior of caret Suba is it triples each time. And these are my raw numbers, and it shows that as you double, you expect the running time to triple, and that's what I see. So let's go, let's do that. So if the number of bits in X and the number of bits in Y are both less than some threshold, then we're just going to use grade school multiplication. Otherwise, we'll do caret Suba. That's our blended algorithm. And so you can see the base case is going to depend on the threshold. At what point do you stop dividing your numbers into smaller numbers and just do grade school? And it's been proposed to use 32 bits. I think that's what I've got graphed, which is good. But here's this thing. It says this is possible. This type of blending is possible because caret Suba is divide and conquer. Why is that important? That caret Suba works by dividing, taking a big problem, and solving it in terms of smaller instances of the same problem. Yeah?
Because then you can still solve the smaller instances separately.
Right. The smaller instances are the same problem, and so can be solved with different algorithms, such as grade school. So suppose grade school were really slow, suppose grade school was the asymptotically faster but practically slower algorithm, and you had a better algorithm. Suppose you reverse the roles. It would be hard to do a blending because grade school doesn't split the problem up into smaller problems, but caret Suba does. Yeah?
So caret Suba is done on base 10, right?
You can do it in base 10 or base 2. We're using base 2 here.
Oh, so it works for all bases?
Sure.
The same concept of divide.
All you're doing is use base 10, you use a 10 here. And you count digits, not bits. So let's see what happens. Now, this doesn't quite work right if X and Y are different lengths. Because if you multiply a gigantic number by a really small number, you don't want to have to chop up the big number until you get it down to some threshold. It might be better to switch over sooner. So let's just assume X and Y are the same length, just to make this simple. Okay. Okay, so this is a cutover at 64 bits. So once we get down to 64 bits, both numbers are 64-bit numbers, we're just going to multiply with grade school. Now let's see what that looks like. It ain't better, but still, the numbers have to be really big before the blue line overtakes the green line. So let's understand, why does it look like this? Why does the green line track grade school all the way to 32 bits? Yeah? It is grade school up to 32 bits. Okay? And then at that point, it starts to degrade again. But it doesn't, so here we got this big jump and then we got the steady state. Here we get a smaller jump and we get a steady state. So what do you think the solution would be? How could we improve it still more? Yeah?
Just start doing caret Suba when they cross in this, like when they would cross.
Okay, so it's tempting to say what we'll do is we'll find out where they cross and switch over to caret Suba there. I mean, switch over to grade school there. But where they cross is way out yonder. And so we would never cut over because we wouldn't be multiplying numbers that big. Where's the right place to cut over? Do you think it might work better to cut over not at 64 bits, but 128 bits? How do you find out? You have to test. You have to time it out and see where's the best test. It's an experiment you have to do. So anyway, this is the curve I just showed you. And you can see that it's not changing until you get in here, and then it tends toward 3 again. The doubling behavior tends toward 3. So what I did was an experiment where I took 10,000 bit numbers and multiplied them, and then I used different thresholds ranging from 512 to 2048 in steps of 256. And that's the plot that I got. So for small thresholds, it was expensive, and then it sort of flattened out, and then once I got up bigger, it started to go up again. So I tested a pretty small range. If I tested a larger range of numbers, you'd see a much more pronounced thing. And it turned out that the absolute, the place where the total time was least was at 1280. Okay, so again, just to say what I did was I took that blended algorithm, I plugged in some value for the threshold like 1024. I fired a bunch of 10,000 bit numbers at it, and saw how long that took. I tried it for different values of threshold and found out which multiplied the least in the least time. Now, what's a little bad about the way I did the experiment, that way of determining the threshold? Yeah?
Each trial and error, you could be lucky or unlucky.
Well, it is trial and error, but if you expect it to come down and then level off and then go up. So you just got to make sure when you do trial and error that you cover enough of the range. Yeah?
Doesn't really explain why that particular value gives us the best.
Yeah, it doesn't explain why that particular value works out the best. It doesn't give us any insight there. What about always multiplying 10,000 bit numbers?
Takes a long time.
Well, it takes a long time, sure, but what I determined was that for 10,000 bit numbers, the right threshold is 1280. Because 10,000 bit numbers split to 10,000 and then 5,000 and then 2,500. They split very predictably, and so really a better experiment would try a variety of lengths of numbers and determine the right threshold. But no matter what you do, it's going to turn out to be around 1,000 bits. So that's what that plot looks like now. So it basically tracks grade school for a while, and up to the cutoff, which is about here, and then it starts to win. So the blended algorithm wins there. So it's faster than grade school if you get up to about 2,000 bits. And if you use a smaller cutoff, what happens is, here's a smaller cutoff. It jumps and then becomes steady. The bigger you make the threshold, the smaller the jump is, until finally you get here and it's no jump at all. But if you go too big, then this flips and the red line gets above the purple line gets above the blue line. So that's pretty this is what I call a blended algorithm. And it applies when you have this situation where you have two algorithms, a asymptotically faster divide and conquer algorithm and an asymptotically slower other algorithm, which is faster for small things. So you blend them. Have you seen any other examples of blended algorithms in your classes or your experience? Yeah.
Merge sort and insertion.
Okay, so merge sort, rather than doing merge sort all the way down until you got single number arrays and then merging all the way up, what can you do?
You can create a cutoff and then do insertion.
Right.
sort.
So you can merge until the arrays get to a certain length and just clean them up with insertion sort at the bottom. You can do the same thing with quick sort and insertion sort, merge those. So it's a pretty common thing to do. I mentioned that I looked at the GNU, the Free Software Foundation big integer package once, and it had 4 different ways of multiplying long integers and 3 thresholds. So it used grade school, and then it had caret Suba, and then it had a couple of fast Fourier transform methods. And it would use the fastest one until it got to a certain threshold, then it would switch to the next one, and then it would switch to the next one. And they had even computed the thresholds for different architectures. So depending on what kind of machine you were on, it would use a different threshold from some other machine. So that's my take on blended algorithms there. Okay. Any last questions I could answer about it? Let me make sure. Okay, that's the last slide. What this shows is that all these versions are tending toward 3 because it's the same slope in the end. Okay. One more thing to talk about. I'm going to do that. I'm going to do this. Okay, we're going to talk about a problem called the selection problem. So the selection problem is you're given an array A of length n, and you're given an index I, and your job is to find the element that would be at index I if A were sorted. Okay? So for example, one example of this would be, suppose you want to know the median of a bunch of numbers. The median of a bunch of numbers is the number that would be in the middle if you sorted it. So if you want the median, you have an array of length 100, you'd look for the element that would be at index 50 if the array were sorted. Now, one way to do this is to sort the array and just go get the element at index 50. So that would take n log n time. But you can do better. So let's look at a better way, a divide and conquer algorithm to do selection on an unsorted array. And it's based on quick sort. So here's the idea. You're asked to do quick select on an array A, index I. So find, if you were to sort A, what would be at index I? And so I call quick select and I say, okay, run the algorithm on A, starting at this index, ending at that index, and there's the I we're after. So what I'm going to do is, eventually low and high will meet at I, and when they do, we'll return A sub I. Otherwise, we partition using quicksort's partition algorithm. And then we look at the pivot that was just used. And the pivot tells us, when you partition an array using quicksort, where does the pivot end up? Yeah?
In the indicated files that you need?
The pivot ends up where it's supposed to go. The pivot never moves after that. And you recursively sort the things to the left of the pivot and the things to the right of the pivot. So you do a partition, the pivot ends up where it's supposed to go. You know what index the pivot is at, and by comparing that index, comparing the pivot to the index you're looking for, you can figure out which half of the array to look in for element I. That's a lot to say. Let's just look at an example. So here we're doing quick select for the thing that will be stored in index 4. So we do a partition, and the algorithm I'm used for partitioning is, we're going to use the last element as the partition. So we're going to arrange the array so that everything on the left side is less than 4, everything on the right side is greater than 4, and 4 is in between those two chunks. Okay? So we stick 4, well, what did I do to get from here to there? Okay, I skipped the algorithm, I just showed you the final answer. So we do the partitioning, you're going to end up with that. Partitioning will stick the 4 there, and the 1, 2, and 3 are over here, and the 5, 6, 7, 8 are over there. And 4 is where it would, if you were to completely sort the array, the 4 wouldn't move. That's the property we're after. So how is it that we can, we're looking for what would be at index 4 if we sorted the whole thing. Why can we throw away the pivot and everything that's left at this point?
Because we know it's not going to be involved.
Okay, he said we know it's not going to be involved. What index is 4 at?
3.
It's at index 3. And we're looking for what would be at index 4. Well, this thing, will, if we sort the array, this thing will be at index 3. So this is not the thing we're looking for. And everything over here will be at some index less than 3. So that's not what we're looking for either. So by just looking at the partition, we can throw away one half or the other. Now we're just paying attention to what's left. So again, we're going to do a partition. 6 is our pivot, and we end up like that. So this is index 0, 1, 2, 3, 4, 5. So how can we narrow things down? We know the pivot is at index 5. And, okay, 5 is too big, and these guys are, their indexes are too big as well. So we can throw those all away, and we just end up there. And that's the base case. The low and the high and the index we're looking for all become the same thing. Okay? So that's, essentially, it's sort of like quicksort. You do it, it's just like quicksort until you've done the partition. Then how does it differ from quicksort at that point?
It doesn't perform the sorting.
Yeah?
You just don't bother sorting the path that's not relevant.
Right, you only have to make one recursive call. Instead of 2. Yeah?
Where was the second partition again?
So, okay, so this was, is this what you're asking? This was, well, I'll just go through it again here. This was the original array. We partition around 4, and we get that situation there. That's the first partitioning. That let us throw away that part of the array. Then we do the second partitioning around 6, and we end up here. Okay? That lets us throw away 6, 7, and 8, and then what's left has to be the answer. Okay? So, what's the analysis? What is the complexity of this? Let's see what I'll start with. Let's talk about running time here, in the best case. So what is the best case for quick select?
That is the partition.
Okay, so if you do the partitioning, and you do the first partition, and the index you're looking for is the index where the partition is stored. All right, you're looking for index 7, and the partition is stored at index 7. You don't have to do anything else, you found your answer. So what's the cost of that? The best case for quick select?
Constant.
No, not constant. It's linear because we had to do the partition. First do the partition, then you can stop in the best case. So it's still linear because of the cost of the partition. What's the worst that can happen if you're always lucky enough to split things in half? Each partitioning gives you an exact split in half, but you never can. You have to keep going until you got one element left. You never get lucky with the pivot.
One of the ends of the array?
What's that?
If you're looking at one of the ends of the array?
Yeah, it would happen when you're looking at one of the ends of the array. But what's the complexity? How do we get after that? Yeah.
Would it be log n?
You said, would it be log n? Well, it's not going to be better than linear.
So it'd be n log n.
Would be n squared.
Okay, I've got lots of proposals. What's the way to find out?
Master n.
Write a recurrence and use the master theorem. So that's not something to be avoided. It's something to be thankful for that there is a master theorem. So there's my recurrence. What is the sense of it? Where does this come from? T of n equals T of n over 2 plus O of n. So the time it takes to deal with an array of length n. Okay, first of all, why is the coefficient of the second T 1? Because that only makes one recursive call. I mean, it's in a recursive case. We're assuming that we always succeed in a perfect partitioning, and we split the array exactly in half and throw away half the elements. So that's why the recursive call is n over 2. And what's this O of n for? That's the cost of the partition at the beginning, before you make the recursive call. Okay? So we have A is 1, B is 2, D is 1. So let's see, log base 2 of 1. What's the power to which you raise 2 to get 1? 0. That's less than the exponent D over there, the O of n. So the answer is just O of n. So it's still linear, assuming that you get the nice split each time. Yeah?
How did you know that, or how would you know that you only have to do one recursion? Can you do 2, 3, in the example?
Well, okay, so when this method is called, how many recursions is it going to make? I see 2 sitting right here. So why isn't it 2?
Because it's only going to call once.
Right, it's in an if then else, so it's only going to call one of these at most. So yeah, this can be a confusing point because you look at the text of the method and you see 2 recursive calls, but only one can be called. Yeah.
So the cost of partitioning is not only but moving them to the appropriate halves, right?
Yeah, partitioning, you're sort of moving in from both sides and swapping elements periodically. So you look at every element and you may swap every element, but it's still linear. Okay, so that's O of n. Now, what would be the recurrence if we always get the worst possible luck when we partition? And that would be, we do a partition, and there's nothing to one side of the partition, and everything is to the other side of the partition, and the part we only succeed in throwing away the partition. You just always just unlucky, the way you can get unlucky in quicksort.
So the partition's at the end every time.
Yeah. The partition is always at the end of the array. Yeah.
It would be n log n because it would be the same thing as doing a quick sort.
Okay, he's saying it's n log n because it's the same thing as doing a quicksort. But what's the worst case of quicksort? N squared. We can write a recurrence for this. What would the recurrence be? the time it takes to deal with an array of length n, okay, there's still going to be one recursive call. And there's still going to be this cost of the partitioning. But what is the size of the recursive call? N minus 1. So we're not always so lucky to cut it in half. Maybe we just reduce it by 1 each time. We throw away the partition each time. So our recurrence then, for this case, looks like that. T of n equals T of n minus 1 plus O of n. Now, what does the master theorem have to say about this?
You'd have to just do it again.
Well, can you apply the master theorem to this? I got some yeses, I got some nos.
What's the minus 1?
Well, if we ignore the minus 1, then we get a b of 1, and we're taking log base 1. You can't do log base 1. Any power you raise 1 to is going to be 1. So the master theorem depends on there being something we're dividing in by. So this is not in a form the master theorem can cope with. Okay? But we can still cope with it. How do you cope with something like that? Yeah?
We could use the master theorem on the worst case if always have a partition, and then use that t constant in the other one, or would that change?
Okay, say that again.
So we would use the master theorem on the worst case if always perfect.
Yeah.
And then we would get the value of t that we're looking for.
But it's a different t in this case.
Okay.
Yeah. So we can't solve up here and substitute down here. Yeah?
My idea, just looking at this, is we realize we're going to recurse n times, just looking at that. And so we're going to have an n squared.
Okay. So this is a lot like analyzing nested loops. So at the first top level of recursion, you do a linear amount of work, right? N. How much work do you do at the next level of recursion when you do the partition? N minus 1. Next level, n minus 2. Next level, n minus 3. So just add all those up. N plus n minus 1 plus n minus 2. That's O of n squared. So you end up with O of n squared.
So it's the same complexity as quicksort.
Yeah, so just like quicksort can blow up if you get extremely unlucky into an n squared, quick select can blow up and become n squared. What's another thing we could ask? We've got the best case, we've got a couple different takes on the worst case. Average case. And it turns out, I won't show it, but the average case is linear. Now, there is an algorithm that runs in worst case linear time for doing selection. It's a divide and conquer algorithm, but it's not quick select. We won't be doing it. If you're curious, look it up. What it does is it splits the problem into fifths. It's the only thing like that I've ever seen. It actually needs to solve the problem. It splits into 5 subproblems that it solves recursively. And there's a fairly involved analysis to show that it's linear, but it actually is linear. Okay? So that sort of finishes up divide and conquer. Next time, I've got a couple more items I want to do, sort of related, and we're going to switch to graphs.